Hello everyone, this is Professor Ma and this is the introduction to the sections roots and factors. Okay, we had before synthetic divisions and we know that I can put down the coefficients and put down the zeros for the of the divisors and then we can put 2 down and then multiply to a plus is 5, 5 times 4 is 20, and 24. Okay, and then we can put this into the mixed form of a fractional formula, where this is the quotient coming from this part, and then the remainders sits on top of the divisors. Okay, so keep that in mind, we can do this. Okay, now let's recall about factorings and the multiplicity or the order of roots. Okay, suppose here I have a formula of factors and into this on the right hand side, and then obviously has two roots. These are 0 and -1. These are the two numbers you plug in, you will get 0, the roots. And the 0 has order 3 and -1 has order 2 or power or multiplicity, whatever you want to call it. It shows up 3 times, zeros, -1 shows up twice. Okay, so if I can factor, then obviously then each factor like this, I can gain a root x minus c of x minus r, the form of factors. Okay, and now we want to establish the vice versa. That is, okay, if it is a root, if a number c is a root, I plug in, I get 0, then I can factor the polynomial with x minus c as a factors. Okay, so and that's where the synthetic division comes in. Okay, and when I divide synthetic divisions, I can, if I divide a polynomial p of x by some divisor d of x, then I can arrive at a format with the q is the quotients. Okay, and here is the ideas, and because of these divisions, I can clear the denominator, multiply x minus 4 to the other side, and that will be multiplied to 2x plus 5, and okay, and this times that. X times these, x minus 4 times these, multiply across itself, plus the 24, this blue color. Okay, and notice, if I call this polynomial p of x, and if I want to plug in the formula, the number 4, okay, why 4? Because 4 makes x minus 4 0, and I want to plug that into it. And that's the same thing as plugging x equal to 4 on this side. But if I were to plug in x equal to 4 on that side, this disappeared because x minus 4 is 0. What's left is 24. In other words, this number left over is the whatever the formula p is, this polynomial, plugging this number 4. Okay. And so written in algebraic expression, that means p of x is some quotient times x minus c plus this number r, and this number r is precisely the same as plugging in the number c into the formula. Okay, and this is where things then becomes. That's where if we plug in, we get a 0. Well, let's make this first of all a theorems statements. So plugging in, it's the same as the remainders we get in the synthetic division, if you like. Okay, so for instance, if I want to plug in the number 1/2, You know, we're putting 1/2 in here. I have to do 1/2 to the 4th power 4 times that, and minus 2 times 1/2 to the cube. Oops, and so on, so on. Instead of that, we can do the synthetic division to find out the last number r, as the remainder is, and that we can just do this these synthetic divisions, and it's a few steps shorter. Okay. So the remainder is 2. So therefore, plugging 1/2 of p is the same as equal to 2. Okay. We can check that. Okay. In particular, if the remainder is 0, then we have px is equal to the quotient times x minus the number c. So if c is a root, if c is a root, remainder is 0, then the remainders r, remember there's r over here, and that's not there, that's 0. Then therefore x minus c has to be a factor. In other words, here's what we have. In fact, this is a factor theorem that basically it says that the problem now looking for factors. When you try to factor the formula, it's the same thing as looking for number plugging in, make the formula 0. Okay, these are two identical problems. If I get one, I get the other. So here, say, let's use a factor theorem to show that x minus 1 is a factor. You know, how can we do that? I mean, do I have to divide it out to find out that what x minus 1 times what becomes this polynomial p of x? You know, no. All I have to do is plug it in. Okay, check that's the root. You plug in, and in particular, plugging 1. It's very simple into a polynomial. While putting 1, then all these x turns into 1, then the only thing left are the coefficients. That's what these numbers are. So plugging 1 and this comes 0, so r. Therefore, x minus 1 is a factor. So p of x is equal to x minus 1 times some other long, real long polynomial. Okay. So here's the observation. If I plug in 1, and so all the which turns out to be the sum of all the coefficients, the numbers in front of all the x's, you add them up. If that's 0, that means plugging 1, I get 0. That means x minus 1 is a factor. Okay. So I can, what does it mean x minus 1 is a factor? So if I want to factor p of x, I can divide x minus 1, and I get a simpler quotient that I can concentrate on factoring the smaller quotient. Okay, and that's the idea. Okay, so here is a summary. If the numbers coefficient add out to be 0, then x minus 1 is a factor. Okay, so check that x minus 1 is factors. Again, so because they add out to be 0. Okay. And x minus 1 is not a factor of this one, because if you add up 5 minus 7 minus 2, it's not 0. So therefore, x minus 1 is not a factor. Okay, so in other words, you're not going to get this big x minus 1 times some other polynomial q of x. Okay. It's impossible. Now, suppose I have an even degree. Suppose I have a degree, a polynomial, and check this. If I want to check minus 1 or x plus 1 is a factor or not, it's the same as if I want to check if p of minus 1 is 0. Okay, the same problem, right? Now, when of p plug in minus 1, you get 0. Think about this. Okay, if I plug in minus 1, all the even powers, x squared, x 4, x 6, they just change the minus 1 to plus 1 times the their coefficient, the numbers in front of them. If I take the -1, put into the odd power, the third and the fifth, and so on, they change their numbers in the front coefficient to the negative. Okay, so when we plug in, supposed to get 0, what the only way for this to happen is the sum of even coefficients of the even degree is precisely the sum of the odd degree. Okay. What are the even degrees here? These 6 power, and k is 0 degree. That's even degree. So I need to have -2, -4, and the k add together. It's the same as the sum of the odd degree, the 9th and the 7th power, which is 1 + 3. Okay. So the only way for this to happen is k has to be 10 in order for x + 1 to be a factor. Here is examples of a typical exercise or a problem, because we can use visual inspection to check easily factor one, like x + 1 or x - 1, and from there kind of work to factor these things completely. So the first things we do is, you check for roots. It's very difficult to check for roots. The only thing you can check for plus and -1. So let's check for 1 is a root. So by the things we just learned, you add a coefficient, say, oh, it's 0. So therefore, x - 1 is a factor. Okay, what's the importance of that? I can now divide using the synthetic divisions. Okay. So, by the way, we checked the even coefficient and odd coefficients are the same. Cannot be 0. Okay. So we check the x + 1 is also root. So what we can do is I can take the original formula, divide by x - 1. It will divide completely. I get quotients. Then I take the quotient, I can divide by x + 1 also, because -1 is a root. And that will bring me down to a quotient like this. So in other words, what we are saying is that the original polynomial, the factors x - 1, x + 1 times the final quotient that's left. -2, remember we do this one backward, -2, -2x in the column, then that square is a 1x squared. Okay. And then finally the things we need to factor is this part. And this part you can do by the FOIL methods, the guessing method. So this one you have to use a quadratic formula to find out 2 roots. So plug in quadratic formula, so I get 2 roots. Okay, one is 1 + √3, one is 1 - √3. Let me call this R1, R2. Okay. In other words, then x - R1, x - R2 are the 2 factors. So if I factor these further, I will get these final answers where this part breaks down into x - 1 of the roots, x minus the other roots. Okay, so this is how we usually, in the home exercise, how we start breaking down, say, third-degree polynomial, or sometimes fourth degree. Most of them, you can take out an x, or maybe take out a 1 or -1. These are the only easy ones, okay? Unless the problem tells you, say, oh, here is a root that x = 2. They will give you one. In general, these problems are very difficult. So these are made up problems. Okay, so basically, this is the relationship between factorings and looking for roots, and they are the same things. Okay, that's it. Bye-bye. Until next time.